Let's see. Okay, so now we are recording and I will share my screen. Just a second. Great. And then let's return to here. Oh, great. So last week we saw about three different diagnostic horizons, three different subsurface diagnostic horizons that are quite important. And the first of them is the argillic horizon. If you remember very well, that I hope so. If you remember, it's that horizon that express clay eluviation or elutriation or clay formation or clay destruction. So, because of one or more than these processes, uh, you register a difference of clay content between the surface and subsurface horizons. So, the higher clay content at the subsurface horizons induce variations of chemical and physical soil properties. Okay, so I put a lot of effort on the variation of clay penetration, of water penetration, water percolation through these horizons, because it's much more common than that you register very high values of water percolation, of conductivity, water conductivity through the A or E horizons, the surface horizons. And at the B horizon, the water percolation, the water conductivity will be much lower than the surface horizons. And because of this, you can find in some soils perched water tables. But what it's definitely most common in the argillic horizon, it's that you can find clay skins, those shiny surfaces in the surface of pads and aggregates that express the clay eluviation, the clay migration from the surface horizons or the A or E horizons to the B horizon. And that clay surfaces, the clay skins, it's one of the most important characteristics in the argillic horizon. Okay. And we also saw the Candic horizon, and the Candic horizon also express a higher clay content at the subsurface horizon than the surface horizon. But in this case, the Candic horizon, it doesn't register clay skins or these shiny surfaces, the shiny pads, because you don't register eluviation, you don't register clay migration from the A or E horizons to the B horizon. In the case of Candic horizons, these processes are more connected to clay destruction or clay production and eluteration or horizontal migration of clay. So clay is removed from that soil, but the clay is not being migrating from the surface to subsurface horizons. Okay. And also we saw the natric horizon, and the natric horizon, it will also register clay eluviation. So it also register a higher clay content of clay at the subsurface horizons than the surface horizons. But in the case of the natric horizon, this clay migration, this clay eluviation, it's induced by a high content of sodium. So it's more common in semi-arid and arid regions with dry climate conditions, and the salt and especially the sodium precipitation at the surface induce a chemical dispersion of the pads and aggregates. And because of this chemical dispersion, you induce the clay migration from the surface to subsurface horizons. And we saw the diagnostic criteria for each of these diagnostic horizons. Okay, so it's quite important to at least highlight and memorize this main characteristics of each one, because they are quite different between them. As I said, the criteria that fits all the details and check all the rules, you don't need to memorize that, because you can and you should check every time that you are describing a soil. Okay, but of course, it's quite important at least to memorize the definition or which kind of environment or which kind of process are more connected to one or all of these horizons. Okay, so this is really, really important. And let's talk about another horizon that also has a higher clay content than the surface horizon. Is the Glossec horizon. But in the case of the Glossec, it's quite different from the others because in this case, the Glossec horizon express some tones, some fringe, some waves of clay between the horizons. Okay, you register something like you have a mix between the E and the B horizon, as you can see in this case. So we have an A horizon here with a dark color formed by partial decomposition of organic matter and the melanization of the mineral materials. We have an EB horizon here with a sandy texture, something with a yellowish color. We have an E horizon that's very well defined E horizon with a sandy texture and even something with albic materials. You can see the whitish or grayish colors. And below of these E horizons, we have the B horizon. And this first B horizon, the BTX horizon, has some change, have some migrations of material. You can see in some cases some fringe, some tones of material between the horizons. So you have in some cases mixture between the E and B horizons. Okay, it's quite common to see these materials, this kind of mixing in the Glossec horizon when you have a mix between E and B horizons. Okay, so in this case, we have a mix between E and B. This kind of tones, they are formed by different process. Okay, the most common process is that when you see this kind of soils in very in dense forests, it's quite common that in these areas you have very long and depth roots. And when these trees, they die, these roots are partially decomposed. Sometimes they are totally decomposed. And let's say that the space that before was fulfilled by these roots should be empty, but they are not empty. Why? Because of course the gravity induce a migration of material. Okay, so even sand, silt, of course, the heaviest particles, they will migrate from the upper areas to above. So you have some migration of heavy particles as sandy and silt, and sand and silt, they will migrate and fulfill some empty spaces that before was fulfilled by roots. And because of this, you can see these kind of tones of sand material inside or into a clay-rich horizon. And sometimes we can see also the opposite. Sometimes you can see some particles or some parts of an E horizon with a clay-rich material. So you have a mix between E, and B horizons. E and B horizons have this mix. I will show also some pictures. As you can see here, for example, we have in this case, in this BT, you have some zones with this grayish or yellowy, grayish or whitish colors. They are showing that you have some spaces of E horizon inside the B horizon. Okay, so you can see here very clearly the E horizon, and here this starts the B, and definitely here you can see some parts of E horizon. They have the same color Of course, if we was in the field, if we were in the field, we could check also the texture, but I can say you, the texture is the same. So you have the same texture, you have the same structure, you have the same color. So basically you have the same horizon, but parts of the same horizon inside another horizon. Okay, so it's quite common to see this kind of fringe or parts of one horizon inside or into another horizon. Okay, so let's see the criteria to identify a glossec horizon. The glossec horizon, it has at least 5 centimeters of thickness, and it should register an alluvial part that's composed by Albeck materials. You already saw what are Albeck materials, those materials with whitish or grayish colors, but basically light colors that are more related to primary minerals, for example, quartz, okay? And these Albeck materials, they should constitute between 15 and 85% by volume of the glossec horizon. So the glossec horizon basically presents a high content of Albeck materials and an alluvial part of horizon that express clay migration, that express a higher clay content of clay, and these could be an argillic, a candic, or a natric horizons. So you can see that the glossec horizon, it should be connected between alluvial and alluvial parts, between an E and a B horizon. So you only can identify a glossec horizon if you register both alluvial and alluvial parts. You can find an argillic horizon without an alluvial part. You can find a candic horizon without alluvial part. You can find, it's harder, but you even can find a natric horizon without alluvial part, okay? But definitely, to identify a glossec horizon, both should be there. You should find an E horizon and a B horizon to identify a glossec horizon. And in this case, both, they should be mixed in some parts of that material, okay? It's not so common to find these glossec horizons, but definitely you can see them in dense rainforests, okay? And especially when you have sandy soils, okay? Now let's talk about a horizon that's really important, really, really important. And in this case, this horizon, it doesn't register higher clay content at subsurface. The oxic horizon register basically a very, very similar clay content of the subsurface horizon when I compare the subsurface and the surface horizons. Okay, so the oxic horizon usually composes a soil with register similar clay content in all the horizons. So it's quite common, for example, to find an oxic horizon with, let's say, 35% of clay, and the A horizon register 33, 32, even 34, or even 35, the same content. So the clay content that we find in the oxic horizon, it's quite similar to above. So we register in this case the same clay content between the subsurface and subsurface horizons. So it's the opposite of all horizons that we already saw. It's the opposite of the candic, argillic, natric, and glossec. It registered the same clay content between the surface and subsurface. If it's not similar, if it's not the same, it's at least similar, okay? So this, let's say, homogeneous clay content between the surface and subsurface horizons identifies some properties that will be basically the same. So the soil profile has basically similar physical and chemical properties among all horizons. So if the surface horizon can easily be penetrated by roots, or water can go through that horizon, will be basically the same for the B horizon. If the A horizon presents a very low content of bases or of a very acidic pH, probably the oxic horizon will register the same characteristics. So the physical and chemical properties of the subsurface and surface horizons in this case will be much more similar than the argillic, the candic, and the other horizons. Okay, it's the case of the oxic. And something that's quite important to understand the oxic horizon is that it's formed by a deep wefting and a deep leaching. Okay, it's why we usually find the oxic horizons in the tropics. So of course we can find them easily, very, very easily in several countries in Africa, in several countries in South America, in several countries in Asia, in several countries around the tropics, because it's their house. We can find very easily they there because they are formed by wet and tropical climate conditions, basically wet, because I need a lot of rainfall. I really need a lot of water to induce a deep wetting of primary minerals and intense destruction of them. So after an intense destruction of primary minerals, basically what I will find in the sand fraction of these soils will be quartz and all the very those minerals that can be very, very easily destroyed. For example, olivine, pyroxene, even feldspars, they will be not present, or the content of these minerals will be quite low because they are very easily destroyed, and this horizon induce its format only in intense destructions, intense chemical and physical wefting, but basically chemical wefting. Okay, sometimes we can find these oxic horizons in dry conditions, in very dry conditions. Okay, sometimes the precipitation it's lower than 300 millimeters per year, and we can find oxic horizons. But in this case, these oxic horizons, they are more connected to past conditions that induce for an oxic formation and very intense wetting that induced in the past by a wet, wetter, and even hotter sometimes past conditions than today and format that oxic horizons. So yes, you can find them in some cases in dry conditions, but they are more connected to past conditions. Okay, especially before the last maximum, the last maximum glacier. Okay, these horizons, as you can see here, they could register very strong and dark reddish color because they are basically formed by iron oxides. So goethite and hematite are the main one of the main minerals that we can find in these horizons because these two minerals are formed by wefting of primary minerals. So when you have the wefting of amphibolites, of pyroxene, of olivine, what you will form? Goethite, hematite, and they will provide a dark reddish or dark yellowish colors in these B horizons. Okay, and of course you also can find some kaolinite and sometimes a lot of kaolinite. You also can find aloysite. Basically all one-to-one minerals that you can think, they will be very, very common in these horizons. JJ, can I see any kind of two-to-one minerals in these oxic horizons? No, guys, because of the intense wetting and leaching. So all two-to-one minerals are basically all of them will be destroyed during the formation of the oxic horizons. The oxic horizons, they are formed by this intense wetting and an intense removal of silica. This intense removal of silica will destroy all two-to-one minerals and only will induce or preserve kaolinite. Even in some soils, even in some oxic horizons, that the wetting it's really intense, even Kaolinite is not being formed now. Even kaolinite will be destroyed. So even kaolinite that are quite stable mineral, in some cases they could be intensively destroyed, and the content of this mineral will reduce a lot. And in this case, you start to see a lot of gibbsite, aluminum oxide, and it express an intense, quite intense chemical wafering. Okay, so the oxic horizon, every time that you heard this name, this diagnostic horizon, you need to think at the same time intense chemical wafering, an intense destruction of primary minerals, an intense destruction of 2 to 1 minerals. Okay, and of course, because of this, we will register a low CEC, a low cationic exchange capacity. Why? Why? I'm saying that we are destroying primary minerals, we are destroying 2 to 1 minerals, and I only have kaolinite, halloysite, iron oxide, sometimes aluminum oxides. All these minerals, they present a low specific surface, but much more important than this, they express a low amount of negative charge at the surface. So they cannot register, they cannot absorb a high amount of cations, and then they cannot register a high CEC. So the oxic horizon, we register basically low CEC because we don't have minerals with a high specific surface there. Okay. Also, we register low activity clays, so no high activity clays in the oxic horizon. And why? Because we are talking about a horizon with a chemical wafering, an intense chemical wafering, an intense leaching of bases of elements. Okay, so I only will register low activity clays in oxic horizons. Okay, and as I said, a low content of easily waferable minerals. So if I can find some feldspar, the content will be quite low, quite low. If I can find a 2 to 1 mineral, the content will be quite low. Okay, because this specific horizon, it's formed by an intense chemical wafering and intense leaching. This photo expresses another oxic horizon, in this case with a yellow color, a yellow, strong yellowish color, you can easily see. And you can see that usually the oxic horizons express a very large thickness because they could be quite thick. Okay, it's not rare, it's not uncommon to see oxic horizons with more than 4, 6, or even 10 meters. Yes. Okay, I already saw some horizons with more than 50 meters. So it's a lot, guys. It's a lot. Okay. And this also expressed something that's quite interesting for these horizons, because the oxic horizons, they could present very good physical properties. What I'm saying that, why I'm saying that, and why it could be important. Well, it's quite common that the oxic horizons, they are connected to savannas and rainforests. So in this both cases, we have an intense biological activity. For example, termites, ants, spiders, and even the roots of plants, they induce an intense bioturbation of soil. And this intense bioturbation produces a strong structure. And this strong structure, it's connected by voids. So you have a very connected web of voids in all of this horizon that induces very good and very high and fast water penetration. So in these areas, when starts to rain, the water can penetrate through A horizon and achieves the B horizon, and can also be very easily go or through the B horizons. And in these cases, this water can achieve the water table level and feed the water table level. So it's quite common that when we found oxic horizons, we have rivers that can run all the year. So we don't have a very strong dry season. And when we have this strong dry season, even then the rivers stills running. Okay, they can run with a lower level, but they stills there. It's something that it's connected as oxic horizons, and this is something that shows us how is important to preserve them, because they can feed the water table, and because of this they can feed the rivers, and then you have water for all the year, even in the dry season. If we start to degrade the oxic horizons, you will reduce the feeding of water table, you will reduce the feeding of the rivers, and then the dry season will be even more intense. Okay, so let's see the criteria to identify an oxic horizon. The first one is the thickness. The thickness is at least 30 centimeters. Okay, it's higher, it's basically the double when we compare with the majority of horizons. And we are saying that just because, as I said, the oxic horizons, they usually present a very large thickness. Okay, so at least 30 centimeters. And when I'm saying about 30 centimeters, I'm saying just about the oxic horizon. Okay, not about the soil. So just only that specific horizon should register 30 centimeters or more than that. Okay. The texture class or the texture should be sandy, loam, or thinner than this. So I should register a high clay content of clay, at least 15%, okay? And the content of sand is not higher than 70%, okay? So you have a variation of horizons, of oxic horizons, but they never register a sandy texture. Okay, never. Why they don't have a sandy texture? Because to register a sandy texture, you are talking about something that didn't register an intense chemical warfarin, okay, or something that cannot produce a strong structure, or at least a moderate structure. Okay, so we exclude the sandy textures from the oxic horizons, and we consider that the oxic horizons, they can register a loam texture, a silty texture, a clay texture, but never a sandy texture. Okay, the content of minerals that can be easily waterable should be less than 10% in the silt and fine sand fractions. Okay, so between 0.05 to 0.2 millimeters, you should not register more than 10% of waterable minerals, of easily waterable minerals. For example, feldspars, olivine, pyroxene, and others. Okay, so let's think that the majority or the main mineral that compose the sand and the silt fractions should be quartz, one of the most strong, one of the strongest minerals that we have. Okay, and because we are saying that the oxic horizon also should register a strong chemical warfarin, of course, the rock structure should be not present in a higher amount. So the rock structure should be less than 5% in volume, unless the little relics with weatherball minerals are coated with sex oxides, with iron oxides, for example. Okay, so I should not register a lot of parts of rocks, a lot of pieces of rocks, unless these rocks are coated by iron oxides. Okay, why? Because I'm saying that this horizon is formed by an intense chemical weathering. I cannot think about something that register an intense chemical weathering and stills with the parent material there, okay, or at least a high amount of parent material, okay? In a vertical distance of 15 centimeters or more from the upper boundary of the B horizon and 15 centimeters, the clay content should not vary a lot. So this is the opposite of the criteria to identification of argillic, candic, and natric horizons, okay? So if, for example, the surface horizons register less than 15% of clay, the B horizon should register less than 3% more of clay than the A horizon. So let's say the A horizon register only 12% of clay, the B horizon should register 12, 13, 14, but not 15, okay? Because the clay content of the B horizon should be less than 3% in this case, okay? Less than 3% more in this case, okay? If the A horizon register between 15 and 40% of clay, so the B horizon should register less than 20% relative more clay. Is that 1.2 or just I calculate, I share the content of the B horizon, I split the content of the B horizon by the A horizon. And this division should be less than 1.2, okay? So when I when I split this contents, this division, the result of this division should be less than 1.2. And when I have a horizon with more than 40% of clay, so the content of the B horizon should be less than 8% more than the A horizon. So let's say that the A horizon has 40%, no, 42% of clay. So 42% of clay. The B horizon should register 43, 44, 45, 46, 47, 48, 49, but should not register 50. Okay, 50. Because in this case, will fit this characteristic, this criteria. Okay, so you just need to think that is the opposite of the candic, argillic, or natric horizons, okay? So it's the opposite. The clay content between the A horizon and the B horizon should be similar. So I cannot fit that criteria of the other horizons that indicate a higher clay content, okay? The clay content could not be the same, but should be similar, okay? Between A and B horizons. And something that's quite important here is that the apparent CEC of the soil, it's equal or less than 16 centimole charge per clay, okay? So should be equal or less than 16 of centimole charge per clay. How can I do that? I just need to split the CEC by the clay content, okay? And this result should be equal or less than 16, okay, centimole charge per clay. So this kind of math is just something that we do to be sure that we have low activity clays in the soil, okay? If you register higher values than 16, so indicates that your soil, that specific horizon register high activity clays, or at least a high amount of activity clays, and because of this, you cannot identify that horizon as an oxic horizon, okay? So only low activity clays. How can I know that? Just divide or just split the result of the CEC by the content of clay. Okay, we have here two different soils. Okay, so we have the first soil with a horizon, a BA, B1, B2, and the second A, BA, B1, and B2. We have here the depths. So, I'm sorry, it's the same soil profile. It's the same soil profile. So here I have the some of the properties, and here we have other properties. Okay, so basically the same, sorry. Here are the thickness between 0 and 15, 15, 28, 28, 80, 80, 112, or 120, I'm sorry, 120. So you can see that the B horizons, they are quite thick. They are almost 100 centimeters. So yes, could fit very easily the oxic horizon. Let's see the pH. The pH is quite acidic, so indicates that the wafting is quite intense. You can see that the phosphorus content is quite low, and it's quite common in very deeply wafted soils that the phosphorus content is quite low. You can see that the potassium exchangeable potassium content it's also quite low. The sodium content it's similar or quite close to 0 because I cannot identify in the equipment. So also could indicate a deep wafting and deep leaching. The calcium, even the calcium content and magnesium content, they are quite low, except for the A horizon. But in this case, the A horizon could be disturbed or influenced by humans. So of course, I need to ignore it. I just need to consider for the subsurface horizon, of course, from the 15 centimeters to 120 centimeters. Okay, the aluminum content it's high, so yes, this indicates a intense wafting. The hydrogen plus aluminum, so this H plus aluminum it's quite high, also indicated an intense acidification of the soil, so an intense chemical wafting and leaching. When we check here the sum of bases is quite low. When we check the equivalent CEC, when we check this CEC, they are basically low. When we calculate the base saturation, it's also quite low for all horizons. It's below 50%, so indicates a very low base saturation. All horizons are dystrophic. We register a very high aluminum saturation, so indicating that aluminum is the major cation that it's fulfilling the CEC, of course, aluminum and hydrogen. This saturation by sodium, it's 0 because we don't have data of sodium. The soil organic matter content, you can see that's not quite low. And here I have the content of coarse sand, fine sand, silt, and clay. And this data, it's important for us. So now we have the content of clay at the B1 and B2 horizons, okay? So it's basically 70%, and the CEC is here. So I can check, and let's start from the B2 horizon. So what I need to do, I just need to divide the CEC of this B2 by the content of clay, that's here, 70. So 2.42, let's do this math. 2.42, if I split this by 70, and then I multiply by 100. The result will be 3.45. 3.45. 3.45, it's quite low, guys. And of course, it's lower than 16. So yes, the B2 horizon fits the criteria for the oxic horizon. I also can check in this case the increase of clay content in some of these horizons. Okay, so when I check here, it fits 8%. So in this case, because of the increase of clay content, I cannot call B1 and B2 as oxic horizons, because the increase of clay content here should fit 8%. So let's check, should be less than 8%. And here I have 8%, an increase of clay content that fits 8%. But I can check the BA horizon. And in this case, the BA horizon is between 15 and 28 centimeters. So in this case, the BA horizon could fit the criteria of clay content, also could fit the criteria of the CEC per clay, but could not fit the criteria of the thickness. So in this case, the BA, B1, and B2, all of these horizons, they are not oxic horizons. Oh, yes, this is a problem because we need to check all details, guys. We need to be worried about that. It's why I always say that you don't need to memorize everything. It's why I'm always saying don't try to memorize. You don't need to memorize all the criteria. You just need to check them. Okay, so when you open your book with your notebooks, with your notes, you just check, okay, so this soil, this horizon fits all the criteria for the oxic, great. If one of these criteria is not fitted, unhappily, we cannot call it as an oxic horizon. Okay, so just be worried about that. I will, as I said, I will provide an exercise this week with a lot of diagnostic horizons, and after always that you need to identify, you need to be worried about all criteria that are mandatory. Okay, so great. An oxic horizon, it's a horizon that's deeply weathered, deeply leached. Great, and the criteria I can check later, no problem. Let's talk now about an spodic horizon. The spodic horizon is that horizon that express alluvial material too. So you can say, oh, JJ, we already saw the Kendic, argillic, glossic, and natric horizons, and all of them register alluvial materials. Yes, and the spodic also register alluvial materials. So, but in this case, this spodic horizon, it will register increase of clay, but organic and sometimes organic and mineral clays. Okay. Now, in the case of the spodic horizon, what it's migrating, what it's moving is the organic material, the organic clay, that clay that's composed by organic properties, organic components, okay, organic particles. So it's quite common, especially in soils with a sandy texture, a high content of sand, that the organic matter could migrate through the soil profile with the water. So when it starts to rain in an area that you have a sandy soil, the water can easily penetrate and percolate through the soil. So in this case, when water penetrates through the soil, the water can carry some of this organic material. Okay, why? Because sandy soils, they usually produce weak structures. And the weak structure cannot protect organic matter from against moving. So it's quite common in soils with a weak structure, with a sandy texture, that water can easily migrate through the soil profile. And then the water migrates, and the water carries the organic matter, I'm sorry. And then the organic matter can migrate from the surface horizons and concentrates at deep horizons. The organic matter in this case will concentrate in the water table level. So now you have an intense migration of organic matter from the surface horizons to deep subsurface horizons, okay? And this organic matter will concentrate in that specific zone, creating a darkish horizon with a very strong dark color, okay? So it's quite common that in this case you find a B horizon with dark colors, because now the organic matter migrates from the surface to subsurface horizons, okay? And as I said, this is quite common in soils that register a sandy texture, but also it's common in soils that register some kind of vegetation cover with some litter that it's more difficult to decompose. So it's quite common in some temperate forests, that especially the coniferous forests, that they produce a litter that's quite rich in lignite. And lignite, it's quite hard to decompose. So the micro or microbiological activity trying to decompose lignite, they produce a lot of acid. And this acid will react with the clay minerals, destroying them. And then you start to produce a horizon with a low content of clay, even if the soil in the past was clay-rich soil. So you are decreasing the clay content at the surface because the clay is being destroyed by acidity that's produced by microbiological activity. And now that you register a lower clay content, when the water from the rainfall starts to migrate through the soil profile, the water can carry some of this organic matter at the surface to deeper horizons, and then concentrate at deeper horizons organic matter. Okay, in some cases it's also quite common that aluminum and iron, they also can migrate with organic matter. Sometimes the migration of organic matter is not so intense, and then you register reddish or yellowish colors more related to the iron oxides. Okay, so you can register migration of organic matter, only organic matter. You can register migration of organic matter plus aluminum and iron as oxides. And sometimes they register a higher or more intense migration of aluminum and iron, and less or even a very low migration of organic matter. Okay, so both cases, all of these three possible cases, they are connected to the spodec horizons. Okay, this migration of materials from the surface to subsurface horizons. Okay, the spodec horizon, it's composed by spodec materials. Okay, and the spodec materials are materials with register an acidic pH, because it's quite common to find the soils in acidic conditions. They are not common in neutral or even alkaline areas, because we are talking about a horizon that's enriched in organic matter, and we know that organic matter produce acidity. The value and chroma should be low, of course. We are talking about a horizon that is registering darkish colors because of the organic matter. It should register an Naubeck horizon, as we can see here. We should register a horizon that lost something. that lost especially organic matter or clay in the past and induced this clay migration. And now we are registering that someone specific section of the soil lost in the past some clay and organic matter, and some parts that receive it, that concentrate this clay. Okay, some of these spodic materials, they can be cemented by soil organic matter. It's not uncommon to see that, and it's quite nice when you start to dig the soil profile. We can find some of these parts that are cemented. They are cemented by organic matter, especially when the iron content is high. This very strong connection between organic matter and iron can produce some layers that are quite strong and hard. Okay, and of course this aluminum and iron contents, they are more connected to low crystallinity minerals and connection with soil organic matter. Okay, so we don't register a very high aluminum and iron contents, but they could be high. Okay, they are more common very low contents, but they are connected to the organic matter. Okay, so you are not seeing something like goethite and hematite formed as the oxic horizons. No, the aluminum, the iron, they are more connected to the organic matter. So here you already saw all of these pictures. So you can see here an Albic horizon, and here an spodic horizon. Here you can see an Albic horizon, again an spodic horizon, and here an spodic horizon. But in this case, this spodic horizon, it's more connected to iron and aluminum than organic matter. It's why you can see this reddish and yellowish colors. Okay. Here, this one is quite interesting because you can see here an A horizon with, let's say, 50 or 60 or 70 centimeters, a transition between the A and E horizon. Here, a very thick E horizon, sorry, a very thick E horizon with some fringe here. And here the spodic horizon below. The spodic horizon, in this case, you can see some dark colors and even some yellowish colors. So you have spodic materials in this case, and spodic horizons that are connected to organic matter, and some of them that are more connected to aluminum and iron. Okay, it's quite common to find that this spodic horizon, it registers single grains structure. So because of the sandy texture, you register when you check at the microscope that a lot of quartz grains, they are present there. So you cannot see very strong structures in these materials, but they are always coated by organic matter. As you can see here, for example, this crystal, it's amazing. You can see a dark coating around all the grain. Here you can see some dark coatings. You can see some dark coatings here too. It's quite uncommon to see this kind of grain. Like, we basically don't have any coating here or here. The majority of quartz grains, they are coated, at least partially coated by organic matter. Okay, so let's see the criteria to identify an spodic horizon. It should, of course, below an O, an A, an AP, or an E horizon. So it should be below one of these horizons, and it should contain spodic materials, at least 85% in a layer that has at least 2.5 centimeters. Okay, and it's not part of an AP horizon. Okay, so it should register what I told you, this characteristics of the spodic materials. And these characteristics, they should compose at least 85% of the horizon, and it should has at least 2.5 centimeters. You can see that the thickness should not, or it's not necessarily quite thick, because sometimes you can find very thin, very thin spodic horizons. Okay, guys, I love this horizon. I really love that it because the spodek horizons, they are connected to geomorphology. So you can connect the geomorphology and soil genesis at the same time. Why I'm saying that? Because as I said, the spodek horizon is formed by organic clay migration, and this organic clay migration usually stops at the water table level. And the water table level, it's something that's quite important for people from geomorphology. So for example, if you want to understand the geomorphological evolution of an area, something that's quite important is to understand the variation of the water table level. And with spodek horizons, you can take a sample, you can analyze, and you can date and know the variation of the water table through the time, for example. So I really like them because they are quite important to do this connection. Of course, they are not so common as the oxic horizons or the agileic horizons or the candic horizons, but they are common. You can see them, you can find them, okay? The Ortstein, it's a cemented horizon. So in this case, you have alluvial horizon. You have the spodek materials that compose the spodek horizon, but now this horizon is cemented. So you cannot take parts, you cannot break it with your hands or with a knife. You need a shovel or even heavier tools to broke an art sign because it's really, really hard. Okay, it's cemented. As I said, by organic matter, especially fulvic acid and aluminum and irons. So aluminum and iron oxides, I'm sorry. So you cannot see root growing through an art sign, okay, as you can see here and even here. These two photos, they express an art sign, okay? So they are similar to rocks, but they are not rocks, okay? So you can see here the E horizon and below this art sign, a section of the soil that's registered spodek materials, but cemented, okay? The criteria, it's composed of spodek materials, as I said, and at least 50% it's pedogenically cemented, so it should be cemented by the interaction between organic matter and aluminum and iron. It should register at least 25 millimeters, just millimeters, you can see. And the continuous ortstein is 90% or more cemented and has lateral conductivity. Because of this, roots hardly can penetrate. They only can penetrate along vertical fractures with a horizontal spacing of 10 centimeters or more. So the ortstein is something that expresses a cemented fraction, a cemented part, a cemented layer of the soil that roots cannot easily grow. And of course, also water cannot penetrate or easily go through. So it's quite common when you have ortstein, especially if the ortstein is close to the surface, that this soils, they suffer of flooding. So in the rain season, in the wet season, it's quite common that the soils, they will be flooded, 100% flooded. Sometimes the water table is even higher than the surface of the soil because the water cannot penetrate through the ortstein. Okay. We also can see some plastic horizons. These plastic horizons, they will be thin cemented horizons. So basically the same case of the ortstein, but now they are thinner. Okay, so you can see just very thin layers. You can see here a coin, just very thin layers. Okay, like this one, very thin layers that we register as cementation. Okay, so the horizon should be cemented or indurated with iron and manganese and organic matter, with or without other cementing agents. So it's basically cemented by iron manganese, and organic matter. And of course, the penetration of roots will be hard as the Ortstein case. And now the minimum thickness is just 1 millimeter, okay? Where associated with spodec materials is less than 25 millimeters. So the thickness, it's less than the Ortstein, okay? So in this case, it should register just 1 millimeter or more, but less than 25, because 25 or more than this is the Ortstein, okay? Let's see now the gypsic horizon. And the gypsic horizon, it's 100% different from the others. The gypsic horizon, it's express the concentration of gypsum, okay? So we already saw that some app patterns, they can concentrate calcium sulfate, but now let's talk about calcium sulfate concentration at subsurface horizons, okay? So we know that at dry climate conditions, as arid and semi-arid conditions, we can concentrate high contents of sulfur, sulfate, calcium, and then precipitation of gypsum, okay? And gypsum, it registers a whitish color, as you can see here. So this soil profile is quite rich in gypsum, okay? So we have this whitish color. It's also quite common to find gypsic horizons in areas close to the coast and areas that were in the past or they are today in modern conditions affected by tidal water. Tidal water, it's quite enriched in calcium, but also in sulfur. So areas that are affected by tidal water but register dry conditions, dry climate conditions, they can induce the water evaporation, and after water evaporation, we'll have some concentration of gypsum, okay? So this is the main characteristic of gypsic horizons. You can see some photos that I took here. Here you can see the crystals of gypsum very, very easily. Seems like calcite, so it's hard at the field distinguish them without acid. So if you have some hydrochloric acid, you just need to drop some drops at these crystals. Okay, so bring some hydrochloric acid, dilute that hydrochloric acid, please, so avoid any kind of accident. But if you bring some diluted hydrochloric acid, like 1 to 10, okay, of acid and water, you can just drop some drops on the crystals. And if you see some bubble, so, okay, we have calcium carbonate, but you can have calcium carbonate plus gypsum, okay? If you drop and nothing happens, you know that that material is not calcium carbonate and probably is gypsum. But again, you only can be 100% sure after you arrive from the field, you run some mineralogical analysis, some XRD analysis, for example, and then you can be sure, okay, now I'm seeing gypsum, okay? So it's something that, yes, you can have a clue, you can have a very good idea in the field that, okay, probably these are calcium sulfates, but only you can be 100% sure after lab analysis. I'm sorry. Let's go. Okay, the required characteristics to identify gypsy.
Professor,
Yeah, yes,
I'm
yes.
asking questions.
Oh,
Yeah,
sorry, I didn't saw. I didn't saw. Yes, please
okay,
open your microphone.
okay. And how does this groundwater or tidal water contribute to gypsum accumulations in the soils?
Okay, okay. Depends on the characteristics of soil. Okay, soils that register a clay rich content, they are enriched in clay, they are more deeply affected because you have a higher specific surface, you have higher retention of salts, higher retention of cations, and if these areas register dry climate conditions, In Brazil, at least, it's quite common that even in the coast, we register dry climate conditions. In these areas, because of this penetration of water in the continent and the addition of calcium, sodium, potassium, but also sulfur, and if you register higher clay contents, so the tidal water can deeply affect and induce the formation of gypsum. In areas that the soil is more enriched in sand, you will not see gypsum formation, but of course, other properties will be deeply affected by tidal water. Okay, so for example, the electric conductivity will be deeply affected by the tidal water. The content of sodium will be deeply affected by the tidal water. The pH will be deeply affected by the tidal water. So we have a lot of properties that definitely they will be affected by it. But depending on the content of clay and the specific surface and the climate condition, you can induce or will not induce the formation of gypsum. Okay, if you register a wet climate condition, so you have intense rainforest, a dry season that's not longer than, let's say, 3 months, the content of clay is not quite high, so hardly you will achieve the formation of gypsum. But the other properties, especially the chemical properties, will be affected by tidal water, definitely. Okay?
Okay. Okay. And at what climatic conditions these gypsic horizons typically form?
Dry, semi-arid and dry. Semi-arid and arid climate conditions. Okay, these photos, for example, I took in Spain, but very dry regions, like very, very dry. They are quite close to arid climate conditions, so the precipitation should be quite low and the potential evapotranspiration should be quite high, quite high. In Brazil, I only saw, for example, in Brazil, I only saw gypsic horizons once in my life, in an area that the precipitation is around 4 millimeters per year, but you have a very long dry season, for example, 8 months of a dry season, and you register a very high evapotranspiration, and you have influence of tidal water. Okay, so yes, definitely, especially without the influence of tidal water, if you only depends on the parent material to induce formation of gypsic horizons, you definitely need very dry climate conditions. Okay, if the precipitation is average, like 1,000 or 800 millimeters or higher than this, very hardly will you find gypsic horizons, because the gypsum is quite easily weathering mineral, can be very, very easily destroyed. Okay, if the humidity in the environment is high, you cannot preserve gypsum, so the gypsic horizons will be destroyed. Okay. Okay, any other question? No? Great. So let's keep moving. Let's see the required characteristics or the criteria to identify the gypsic horizon. It should be at least 15 centimeters of thickness or more than this. It's not cemented by gypsum, okay, with or without other cemented agents, so should be not cemented, okay? And if you register some cemented parts, they should be less than 5 millimeters of thickness, or is cemented, but because of the lateral discontinuity, roots can easily penetrate along vertical fractures or vertical voids in a spacing of less than 10 centimeters. So you can see that this gypsic horizon should be a horizon that's not cemented, or if you register some cementation, the roots can easily penetrate through the gypsic horizon, okay? So it should be something that the roots cannot find anything that could be hard or harder to avoid the root penetration. Of course, you cannot see a lot of roots here because, as I said, dry conditions, remember? So the roots will be not very abundant, but they can easily penetrate through the soil if they want to, if they need to, okay? And I need to find at least 5% or more of gypsum by wave, okay? And has 1% or more by visible secondary gypsum, like the crystals, as I'm showing you here, okay? These are secondary crystals of gypsum. Or some spots like this, spots you can see, they also are secondary gypsum, okay? So you see some spots of whitish color. And has a product of the thickness in centimeters multiplied by the gypsum content of 150 or more. So I need to do a math, okay? Again, if I have a horizon with 30 centimeters of thickness and I have, for example, 5% of gypsum, yes, it qualifies a gypsic horizon, okay? So I need to find result that I multiply the thickness and the content of gypsum, and it should be equal or higher than 150, okay? And of course, in this case, I need to consider about the crystals of gypsum, okay? So at least 1% or more of visible gypsum, okay? And no cementation, or if I register a cementation, the cementation should be very, very thin or small pieces, small parts of cemented bodies, okay? So again, please, you need to consider all the mandatory criteria, and the mandatory criteria, they are connected by and. So this one, it's connected to this one and connected to the others too. And we have the petrogypsic horizons. The petrogypsic horizon, it's also a horizon with express concentration of gypsum as the gypsic horizon, but now we have a cemented horizon. It's basically that, it's quite simple. So the concentration of gypsum was so intense that induced the partial or total cementation of the horizon, and roots cannot easily penetrate through that specific section. Just that. So the intense gypsum formation fulfill basically all the voids or the majority of the voids, and because of this intense fulfilling of voids, the material is quite dense. So the material is quite cemented and the roots cannot penetrate through the horizon, okay? I never saw a petrogypsic horizon in my life, but I think that could be quite interesting to see, okay? Of course, which climate conditions? Dry, guys. Very, very dry climate conditions, because they need to induce something that's an intense formation of gypsum and a very strong cementation of that soil. The criteria: cementation or induration by gypsum, okay, with or without other cementing agents, no problem. Because of the lateral conductivity, some areas can have some root penetration, but the roots only can penetrate through fractures that have a distance of 10 centimeters or more than this. It should register at least 5 millimeters of thickness, so quite thin, okay, as the Ortstein, like the Ortstein, sorry. And here it should has at least 40% or more of gypsum. So the content of gypsum here, it's much higher than the gypsic horizon, of course, because now I'm talking about cementation, okay, something that's quite intense. Now we will talk about the calcic horizon. The calcic horizon, it's a horizon that also express the clay, not the clay, I'm sorry, the concentration of something, but especially calcium carbonate, okay? So express some calcium carbonate concentration. Okay, some cases we also register an increase of clay content, and because of this increase of clay content, we also can induce a concentration of calcium carbonate. Okay, so of course, calcium carbonate and other carbonates, and why we are always talk about calcium carbonate, just because it's the most common, okay? But calcite, dolomite, and other carbonates can be present, no problem. But the calcium carbonate is the most common because it's the most hardish mineral between the carbonates. Okay, between the carbonates, it's that one that hardly will be destroyed. Sodium carbonate, magnesium carbonate, potassium carbonates, they are very, very easily weathered. Okay, so the calcium carbonate is more common, and also because calcium it's also more common than the other elements. So yes, it's more common to find calcium carbonate in the soils, especially in the calcic horizon. We are not talking about cementation, so you can see these white spots, these white dots, but without cementation. Again, the roots can grow through the horizon as the gypsic horizon. Okay, and you can see here my finger, and you have the same whitish spots as the gypsic horizon. And as I told you, you easily can differentiate the calcic and the gypsic horizons usually using acid. So just drop some acid, and if you see bubbles, if you see some reaction, great, you can register calcium carbonate, you can register calcic horizon. And as I said, you also can see here in the same depth at the same horizon, both cases. You can see the gypsic and the calcic horizons, but at least if bubbles, if reacts, at least the calcic horizon is present, okay? So in this case, take a sample, send to the lab, run some XRD analysis, and check if you also can register the gypsic horizon, okay? So you can see here in more detail a photo of this specific section of this specific horizon. That's the calcic horizon, a horizon that express secondary precipitation of calcium carbonate. Where can I find this kind of horizon, JJ? Dry conditions, guys, is the same, okay? Because the calcium carbonate, it's a mineral that can be easily destroyed in wet conditions. So hardly I will see a calcic horizon in a wet and hot climate condition under, for example, rainforest. Oh, quite hard. Okay, it's more common to see in temperate forests, grasslands, savannas, where the precipitation is not quite high, and I register a long dry season. And of course, to induce the formation of a calcic horizon, it's quite important that in that specific area, I have a source of calcium and carbonate. And then it's more common to find calcic horizons in soils formed by weathering of limestones or other rocks that are enriched in calcium, okay? But basically, the most common case is, of course, limestone. So the weathering of limestones in dry conditions could favor the formation of secondary calcium carbonate and then the formation of calcic horizon. Okay, I'm always saying that maybe or can because it's not like a rigid structure. Okay, of course, some soils formed by limestones, they cannot form calcic horizons if the climate conditions it's too wet, or if the leaching it's quite intense, or if the dry condition it's not, if the dry season is not too long, or if the vegetation cover it's too dense or something. If something between the soil formation factors affect that the calcium and the carbonate concentrations, and it's not allowing, it's not well yielding the formation of calcium carbonate, Okay, no problem. You need to consider that, yes, the majority of soils formed by limestones, they could form calcic horizon, but it's not mandatory. It's not a rule, okay? Okay, so now let's see the required characteristics to a calcic horizon. The thickness should be 15 centimeters or more. It should register one or more of the following. Okay, so A or B. Okay, so letter A, 15 or more of calcium, equivalent calcium carbonate. Okay, so this is a lab analysis that we measure the content of calcium carbonate. And so if the calcium carbonate content is quite high, so in this case, high, like 15% or more, the calcium carbonate content should be 5% or more higher than that of an underlying horizon. So the calcium carbonate content in, for example, the B horizon should be 5% or more higher than the C horizon, okay? Or another B horizon, but should be higher than the underlying horizons, okay? And should has 5% or more by volume of identifiable secondary carbonates, as this photo that I'm showing you, okay? These spots of secondary carbonates. Or, so this, or 5% or more of calcium carbonate. So when I run some lab analysis, I can measure the content of calcium carbonate, and I see that's 5% or more, but less than 15%. And I register less than 18% of clay in the fine earth fraction, and meets the criteria for a sandy skeletal, coarse loam, or loam skeletal particle size class. So the clay content is not high and has 5% or more of secondary carbonates, as I show at you. That's 5% or more higher than that of an underlying horizon. So I can see more secondary carbonates than the underlying horizons, okay? So in this case, I have a higher content of calcium carbonate, so I have less rolls, let's say, and here the calcium carbonate is lower than here, so I have more rolls. If I fit this one, okay. If I fit this one, it's okay too. Okay, so this one or this one of these two criteria will be enough to identify the calcic horizon. And it's not cemented or indurated, because we will see another horizon that has cementation by calcium carbonate. And if you register some cementation, so the cementation, it's not avoiding root penetration, so the roots can penetrate through some fractures, through some voids that are quite common. So the distance between these voids, it's less than 10 centimeters. The cemented layers or parts, it's less than 1 centimeters of thickness, and consists of some laminar caps, okay, underlying by a lithic or paralithic contact, okay, so they are more connected by a partial decomposition of rocks, and a cemented, or I'm sorry, the cemented layer is less than 10 centimeters of thickness. So if you register cementation, this cementation is not strong, the roots can easily penetrate from it, and the thickness is quite thin, or at least thinner than 10 centimeters, okay? And now let's talk about a horizon that's cemented by calcium carbonate and other carbonates. So we have carbonate, especially calcium carbonate concentration, but now this concentration, it's so intense that part of the soil is cemented, as the same case, like the case of the petrogypsic horizon. Here we have a very strong cementation because a very strong concentration of a secondary mineral, in this case, carbonates, but basically calcium carbonate. So this photo, it's amazing because you can see this horizon below 40 or 50 centimeters. That's completed, cemented by calcium carbonate. It's amazing, guys. I took a piece of this horizon, and so you can see in my hand that we have some soil, okay, like here, and we have some pebbles, some sand grains, some coarse grains like gravels, but everything is fulfilled and coated and cemented by calcium carbonate. So very dry past conditions induced an intense cementation of the soil and produce a petrocalcic horizon at this specific depth. Okay, and I know that we have calcium carbonate here because I just dropped some acid and I can see the bubbles. But again, I can register a petrogypsic and a petrocalcic horizon at the same time, at the same depth, but I only can confirm this running some lab analysis, okay? The criteria to identify a petrocalcic horizon said that horizon is cemented or indurated by carbonates with or without silica or other cementing agents, okay? Because of the lateral conductivity, the roots cannot easily penetrate. They only can penetrate along some vertical fractures or voids, and these fractures or voids, they have a large distance between them. Okay, so this distance between the fractures should be 10 centimeters or higher or more than that. And the horizon has a thickness of 10 centimeters or more than this, or 1 centimeter or more than this if we have just laminar caps. So horizontal horizontal layers that are quite thin, okay? Just 1 centimeter will be enough. So you can see that this criteria, they are the opposite of the calcic horizons. So they are this thickness of the cemented horizons should be thicker than the calcic horizon, okay? If we register cementation by gypsum, if we register cementation by iron, organic matter, aluminum, if we register cementation by calcium carbonate, we also can register cementation by silica. So silica can also cement some subsurface horizons and form what we call as duripan. So you can see some layers here that are silica enriched layers that express cementation by silica. Okay, so this is quite interesting in this specific case because this duripan, it's also only formed in the very dry climate conditions. So in some areas with semi-arid and arid climate conditions, in very dry areas, you register some soils that could be formed, for example, by the wafting of granites. And so granites, they are enriched on feldspars. And the feldspars, the wafting of these feldspars, an incipient or limited wafting of these feldspars can release some calcium, potassium, magnesium, sodium that will enrich, improve, increase the pH. So the pH of the soil, especially at the surface, could be quite high because at the surface, I also can register some salt concentrations. Do you remember? So the water can penetrate through the soil, and because of the very dry condition at subsurface, the water can migrate from the subsurface, achieve the surface, and induce some salt precipitation. This salt can induce a very high pH and also induce the chemical dispersion of beds, and at high pH, especially at very high pH, higher than 8, the silica can be very easily destroyed, very easily destroyed. So you can destroy clay minerals, especially the silicates, very easily if the pH is quite high. So this silica will be free. They are not bound to other elements and producing or creating minerals. And because of the water percolation through the soil profile and because of the gravity, the silica can migrate from the surface to subsurface horizons. And the silica will stops at the water table level, or will stops where the clay content is higher, or will stops where the pH is lower than 8. So if you does not register salt concentration, salt precipitation, so it will register precipitation, a reprecipitation of silica, because silica is only free to move at very high pH higher than 8, as I said. So if the pH drops to 7, 6, or even lower than this, the silica will reprecipitate as something, okay? So the silica stops to move, stops to migrate, and then you can now fulfill the voids with silica and induce the cementation of a part of a soil, a section of the soil with silica. In this case, we call this section as Duripan. The Duripan is formed by the cementation of silica. And as I said, the cementation of silica comes from a soil that with a very high pH at the surface induced the destruction of clay and the silica migration from the surface to subsurface horizons. They are not the clay migration, it's silica, only silica migrating. As the calcium, potassium can migrate, the silica also can migrate, but the silica only migrates at very high pH. I heard that someone raised their hand. Can you open your microphone?
Yes, good afternoon.
Good afternoon.
Sir, I'm sorry. I want to more clarification about that Duripan and the Hadipan. Is that the same or is any differences?
Okay. Great. Good question. Okay. The hard pen and the Duripan, they are differences, but basically of classification, I'd say in this way, okay? The hard pen, it's more like, it's not a diagnostic horizon, okay? The hard pen, it's more like a word that we use to identify a horizon that has cementation, usually cementation by silica, but it's not the name that soil taxonomy uses. Okay, so basically that. So in the soil taxonomy, we call cemented horizons cemented by silica as Duripan, okay, not as hardpan. But yes, they are the same. They are not 100% the same just because the people decided to use this specific word, okay, Duripan. So it's just another word to call the same material, but in the soil taxonomy, we use Duripan, okay? So people that use use it to other systems, they could use hardpan, but at soil taxonomy, we choose Duripan, okay? But the formation is basically the same.
Okay, thank you, sir. It's all right.
Welcome. The criteria to identify Duripan should register cementation, so more equal or more than 50% of the volume register cementation, okay? When I put less than 50 of some materials of the soil, less than 50% of the volume of this material, air dry fragments, slakes in 1 mole of hydrochloric acid, even during prolonged choking, should be slakes. So when I put some soil with hydrochloric acid, I cannot see that these fragments, they are being destroyed, that they are being dissolved, okay? Why I'm saying that? Because, of course, silica that's cementing this duripan, the silica is not destroyed by hydrochloric acid. It's only destroyed by very high pH. So when I put some fragments of this cemented horizon with acid, and even if I keep there for some hours, no problem, that horizon keeps stills like a rock, stills like a cemented horizon, because that fraction, that horizon, that piece of material cannot be destroyed by acidic pH. But when I put that same material in contact with potassium hydroxide or sodium hydroxide, I will register an intense destruction of that fraction. I will register an intense destruction of that material. So when I took a piece of duripan and I put it in contact with acid, we'll keep the same. I don't register any destruction of that material. But when I took a piece of duripan and I put it with something that could produce a very high pH, like potassium or sodium hydroxide, yes, I will register a strong destruction. Okay, so at least 50% of that material will slake, will be destroyed. Okay, it should register evidence of accumulation of opal or other forms of silica, such as laminar caps, coatings, lenses, or partially filled interstices, for example, like fulfilling of voids, bridges between sand coarse grains, or coatings or rocks, or power rock fragments. So I should register any kind of coating or fulfilling of silica, okay? And because of the lateral conductivity, roots cannot easily penetrate, only penetrate from along some vertical fractures. And these fractures, they should have a distance between them of 10 centimeters or more than that. Okay, so I cannot see a lot of roots penetrating and growing through this duripan, okay, as the other cemented horizons. Okay, so let's say that the only difference, or the most important characteristic of this specific horizon, is this section, the point 2, that this material is not dissolved by acid, but it's quite dissolved by neutral or alkaline solutions. Okay, and we also have the fragipan. The fragipan, it's similar to the duripan, but now I cannot easily broke the material. I can easily broke the material. Okay, it's something that is not so hard as the duripan. I can see very easily some roots growing and some water penetration because the cementation is not so strong. Or the duripan in the past, the duripan format in the past, but now this duripan is quite degraded. The destruction of the duripan can form a fragipan, okay? So the fragipan, it should register at least 15 centimeters or more than this of thickness. And the layer, that section should evidence some pedogenesis within the horizon, or at the minimum on the faces of structure units. So I should register at least a little of pads, a little of aggregates. Okay, this is quite important to avoid to call, for example, a supraleaf. I can differentiate a supraleaf from a fragipan, and the layer has very coarse prismatic, columnar or blocky structure of any grade, has weak structure of any size, or is massive. The separations between structural units that allow roots to enter, to penetrate, have an average spacing of 10 centimeters or more, or they are frequent. So I can see a lot of roots growing very easily through that specific horizon in the horizontal dimensions. Air dry fragments of the natural soil fabric, 5 to 10 centimeters in diameter from more than 50% of the layer slake when they are submerged in water. So I don't need to put them in alkaline solutions anymore. Just water will be enough. Okay, so I just put some pieces of soil in water, and I can see that they will slake, they will be dissolved, let's say in this way, when I put this material in water. Okay, the layer has 60% or more of the volume, a firm or firmer rupture resistant class, a brittle manner of failure or near field capacity, and virtually no roots. So 60% or more of the volume should be quite hard to break using my hands. Okay, so of course I can easily break with my knife, with my shovel, but my hands, I will feel something that quite hard. And the roots, they can penetrate, but of course it's not something like an oxic horizon or an agylic or a candic horizon. They can penetrate, but they only can penetrate through the voids or the fractures. Okay, and of course I cannot see any evidence of reaction with acid to show that that material does, it shows not any concentration of calcium carbonate. Okay, and let's see the last horizon, the last diagnostic horizon, the Cambic horizon. The Cambic horizon, it's the last diagnostic horizon that we have, and should be the last diagnostic horizon that we think when we are classifying a horizon. I think that someone raised their hand. Yes, please. No? No? I think that someone... No? Okay, sorry. I thought that someone raised it. So, okay. So the Cambic horizon should be the last diagnostic horizon that you will think that when you are standing a soil, when you are trying to classify a soil. And why? Because the Cambic horizon, all the properties, and maybe the most important property is that this specific diagnostic horizon, it does not fit the others. So I only can call a section of the soil as a Cambic horizon if that specific section cannot fit the criteria, at least the mandatory characteristics, and properties of another diagnostic horizon, of the other diagnostic horizon. If a section can fit, for example, the calcic or the gypsum or the oxic or the candic, I cannot call that section as a Cambic horizon. So the Cambic horizon only will be that section that it does not fit the criteria for any other diagnostic horizon. Okay, we have just one exception for this, and I will show you in the next slides, but you can memorize like this. The Cambic horizon is that section that does not fit the mandatory criteria of the all other diagnostic horizons. And because of this, now I can think, okay, maybe this could be a Cambic horizon. And I will check if this section fits the criteria, if the definition of the Cambic horizon. So a Cambic horizon comes from Latin or Spanish that means change. So this Cambic, it's something that's changing from something that's not a very good structure, is not very well transformed, or very, very limited weathering and leaching, to something that will be in the future more weathered and has a stronger structure, but it's in the middle. Okay, so I like to think that the Cambic horizon, it's like a teenager. So it's not a kid anymore, but it's not an adult. So it's in the middle between an adult and a teenager, an adult and kid, a baby, or even a child. So it's in the middle. So that section does not know very well its potential, or doesn't know very well what that person wants to know or be. Okay, so it's something that's changing. We have some properties that are quite connected. Limited buffering and soil formation, but we already can see some soil formation. We can see some soil that was formed, some structures, some pads, but it's not an intense formation of pads. It's not a deep formation of soil. So it's something that's in the middle, okay? We have some mineral destruction. So we have the buffering of primary minerals, for example, calcite, gypsum, feldspars, olivine. We register some leaching. So this Cambic horizon cannot evidence any concentration of, for example, calcium carbonate or gypsum or silica. Cannot register that. Okay, so you need to register leaching. You need to register losing of material. The color should be different from the color of the saprolith. So, for example, in this photo, you can see this pinkish, this pink color. It's connected to the C horizon. And here we have a B horizon with some structure, but it's a very thin B horizon. And the structure, I'm telling you, is not very well formed. So this is a Cambic horizon, basically a Cambic horizon, okay? Because the structure is not intensively formed. I can see a difference of color between this horizon and the C horizon. And it's leached. It doesn't register any concentration of calcium carbonate, gypsum, or silica. I don't register a very large thickness. I don't register concentration of clay. It's Cambic horizon. It should not register clay eluviation. So the content of clay between the B and the A horizons should be quite similar as the oxic horizon. So like the oxic horizon, the clay content should be quite similar and in the A and B horizons, okay? So the B horizon should not register very higher clay content when I compare the A and B horizons, okay? So because of this limited evolution, it's quite common that the Cambic horizon registers several different properties and different shapes and different colors. So you can see here, this is a Cambic horizon, and this is also a Cambic horizon, okay? You can see a lot of spots, white spots, and these spots, they are not calcium carbonate, they are not gypsum, they are feldspar grains. So we have a lot of feldspar grains here, and this feldspar grains shows that the buffering exists, but is not so intense. And as I cannot see any concentration of secondary minerals, I can call this as a Cambic horizon. So let's see the characteristics of a Cambic horizon. It is an altered horizon that has 15 centimeters or more of thickness, okay? If it is composed of lamellae, the combined thickness of the lamellae should be 15 centimeters or more, and it should register a texture that's very fine sand, long, very fine sand, or thinner than this. So I cannot register a very high content of sand, should be at maximum of 70% and at minimum 15% of clay. It should register soil structure or the absence of rock structure, including fine stratifications, okay, that are 5 millimeters or less of thickness in more than 1/2 of the volume. So I can see rock structure. I should see rock structure because of the buffering is not so intense, but I should not register a very high content of rock, because if I register more than 1/2, maybe that material is not a B horizon, okay, and then could not be a Cambic horizon. Also, it should register additional evidence of alteration in one of the following forms. For example, in wet soils, in flooded conditions, with aqueous conditions. What are aqueous conditions? Aqueous conditions, they are connected to flooded soils. Okay, so flooded soils within 50 centimeters of the soil surface or artificial drainage, and all of the following. I should register colors that do not change on the exposure to air. So I took some samples and I will expose those samples to air, and there's no changing of color. Okay, the dominant color, moist, on faces of pads or in the matrix as follows. The value should be 3 or less in neutral colors with no hue, that letter N, and 0 chroma, or the value should be 4 or more than that, and the chroma should be 1 or less than there, or any value, the chroma should be 2 or less than this, and I should register some redox concentrations, some gray colors that express material that's influenced by aqueous conditions, by flooded conditions, okay? Or in soils that register a better drained soils, in better drained conditions that are not flooded or doesn't register aqueous conditions. They does not have the combination of aqueous conditions in the first 50 centimeters of the soil surface. They are not artificially drained, okay? And colors, moist as defined in item 4A above as in the wet conditions, and has soil structure or the absence of rock structure, including fine stratifications in one more than 1/2 or of the volume and one or more of the following properties. So I should register pads, aggregates, and I should register a low content of rock structure and higher chroma, higher value, rather hue, or higher clay content than the underlying horizon or an overlying horizon. So I should register a different color from the when I compare to an underlying horizon, and I should register an evidence of the removal of carbonates or gypsum. So if that soil is enriched in carbonates or gypsum, the horizon that I want to call as a Cambic horizon should register some reduction of the content of that, destruction and removal of carbonates and gypsum or gypsum. It should also register properties that does not meet the requirement for anisotropic, histic, pholistic, melanic, molic, Pelagian, or umbric patterns, and also should not fit the criteria for a duripan, fragipan, argillic, calcic, gypsic, natric, oxic, petrocalcic, petrogypsic, plasic, salic, spodic, or sulfuric horizons. So you can see that it does not fit the criteria for the others, but it's quite nice to see that the ocric pattern is not here. So the ocric pattern is the only exception that we can have that fits that of a soil that could fit an ocric pattern and at the same time a Cambic horizon. So the same section of the soil I can call as ocric pattern and Cambic horizon. Okay, the first I don't remember very well, but it's reading in the manual now, but as I can remember, the first 15 centimeters, 15 centimeters of the Cambic horizon will be called as an ocric, but will be an ocric and Cambic horizons at the same time, okay? And as I said, the Cambic horizon cannot fit the criteria from any of this. So if you fit the criteria for any of these horizons, so it's not an oxic, okay? The cambic horizon is also not part of an AP horizon, a horizon that has some human influence and does not have a brittle manner or failure in more than 60% of the matrix. Okay, so I cannot register any strong influence of humans. Guys, these are the diagnostic horizons for the soil taxonomy. Okay, now I can see a hand. Naji, do you want to ask something?
Yes, thank you so much, Prof, for the wonderful presentation so far.
Thank you.
The cambic diagnostic horizon, you are giving some characteristics or requirements, but I would like more explanation on the section where you describe that the overlying layer and the underlying layer of the cambic section, the color differences. At what percentage can we be able to differentiate that, okay, this section that the overlying layer has also type of color and the underlying layer has also type of color? What percentage? Is there any limitation on how to recognize that?
Yeah, but it's not a percentage.
Okay.
It's something like a value. Like here, for example, let's say that you identify a color of the underlying horizon, and something that you think that could be a cambic horizon. Okay, the cambic horizon should register like any kind of color. For example, let's say in well-drained, let's see the well-drained conditions because it will be easier. Okay, in well-drained conditions, or at least soils that are not flooded, they should register higher chroma or higher value or rather hue or a higher clay content. So, for example, when we return to here, let's say here in this case, okay? So this horizon has a higher value and a higher chroma than this horizon, okay? Because you can see that this horizon, this pinkish color, it's a light color. Do you agree with me? That's a lighter color than this?
Yes.
Yes, great. So I register here a darker color than this. This darker color is connected to a higher value and or a higher chroma than this. So if I register a higher value and or a higher chroma, so I'm saying that this horizon, it fits this criteria of this one, a higher chroma or a higher value or rather hue or even a higher clay content than the underlying horizon. So it's not a percentage, it's just a comparison, okay? So let's see, for example, that this color, this section with this pinkish color, I will say that I'm just kicking, okay? I'm not saying that's this color, but let's say that this specific section with this pinkish color, it's 5YR 4/4. Okay, and when I check this, I will check 5YR 5/6. So I'm registering a higher value and a higher chroma than this, okay? Or for example, I can register a redder color. So I can register just the same value or the same chroma or even lower than that, but rather hue. For example, I see here like 5YR, and here I'm saying that this is 2.5YR. So I have a redder color here than this. So yes, I will call this as a cambic horizon too. It's just to differentiate that you have here some wafering that now induce some pads formation, some aggregates formation, and this wefring it's strong enough to differentiate a section of the soil from saprolite. So the color is just to mention that, okay, this is just the wefring of rock without pedalization, without soil formation. This is just wefring of rock. And here we have soil formation. Here we have soil formation. So we have a distinguished color, a color of the soil that we can easily distinguish from just wefring. Okay? It's clear now?
Yes, thank you, Prof.
Welcome. Is there any other question? Is 100% okay? Okay, great. So we finished, as I said, all the diagnostic horizons. And I know that's a lot. Okay, because we have like here 75 slides. I will stop for now, and I will share with you in the next few minutes a list of exercises, and I will ask you to use this time trying to identify the app patterns and the subsurface diagnostic horizons. Okay, yes, please, you can send me the answers and all the answer, how you find that specific diagnostic was found, or which kind of app pattern do you think that's more correlated to that specific soil. But please, you can also write a little bit and try to explain why you achieved that specific answer. Okay, so, considering, for example, considering that this specific horizon has calcic, secondary calcium carbonate concentration, I believe that's more connected to calcic horizon. This horizon has a very low CEC, a very large thickness, very low activity clays. So, and the clay content, it's quite similar between the A and B horizon. So this horizon should be an oxic horizon. So try to answer in this way, try to fit the criteria that specific horizon has, and explain to me why you use it and which criteria did you use it. Okay, and of course, as I said, the OCREC app pattern and the Cambic horizons should be your last options, but of course I will include some of them in the exercises, so you need to consider in some cases all the options. Okay, so please just open in your screen or have a hard copy of the soil taxonomy and check one by one of the diagnostic horizons, the app patterns and the subsurface diagnostic horizons. Then you will find the answer. So please avoid just to answer like, okay, this is the oxic horizon, but explain why do you think that this specific horizon is an oxic horizon. Okay, because then I can understand if you deeply understand the soil taxonomy, or if you still have some questions, or if you are wrong, I at least can understand what I should highlight before start the classification at the order level. Okay, and we start to talk about the orders of soil taxonomy. So please take your time to do this. You have 1 week to do all the exercise and try to answer all the questions. I will share also the answers in the end of the document. So I will just skip one page, so you avoid to see the answers before end the exercise, but they will be there and you can check your answers. But please send me, especially if you have any doubt, because if you have any doubt, I need to know and I need to be sure that's 100% okay. Okay? Any doubt about that? Okay, so I will share this on our
Hello, sir.
folder. And okay, great.
Hello,
So
sir.
just before we, oh yeah, yes, yes.
Sir, I have doubt about this exercise. Please, can you repeat the statement again about the exercise you are talking about?
Yes, yes, of course, of course. I will share a list of exercises, a list of soil profiles, and I will ask you all to classify the app patterns and the subsurface diagnostic horizons. Okay, I will share a photo. I will share some morphological properties. I will share some chemical and physical data. And you just need to answer about the app pattern and the subsurface diagnostic horizon. So just say to me, oh, JJ, the soil profile number 1 has a Molech app pattern and a calcic horizon. And why? The most important part of this exercise is why. Why do you think that this specific soil has a Molech app pattern? Oh, JJ, I think that this horizon, it's a Molech app pattern because the organic carbon content is high, the color is dark, it registers a soft consistence, the calcium carbonate, it's high, let's see, all the pads and aggregates has a structure that's connected to this specific horizon. So all the properties, especially those that are mandatory, are fitted. And I think that this subsurface horizon is a calcic horizon because I can see in the description and in the photo some spots of secondary calcium carbonate. The pH is high. The calcium carbonate equivalent is quite high, and everything else, all the thickness, all the properties are fitted. So you need to explain you choose that specific horizon. So please do not reply just, oh, I think that's Molech. No, explain why you think that's a Molech, a pattern. Okay?
Okay, sir. Are we going to choose the? Are we going to choose the horizon ourselves?
Yes, 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 yes. I will put an exercise and you need to think about all the possibilities, all the patterns, and all the diagnostic horizons. And for each soil profile, you need to classify for app patterns and subsurface diagnostic horizons for all cases. Okay?
Okay, I get it. Thank you, sir.
Great, great. I will share again here in our chat the link for our folder, so you can find there all the material for the course. I will share the slides now, and I will share the list of exercises in this folder. Okay, so please check it. In the next, I think 10 or 12 minutes, I will put in the file there, and you have all week to answer these questions, okay? And guys, during the week, if you have any doubt, just let me know, okay? Just, oh, JJ, I cannot find the answer, or I'm in between 1, 2, or 3 different options. Let's talk why you are not finding the right answer, and I can help you with that, okay? But of course, try to find the answer. Think a little bit, check your notes, check the system, and you can find the answer. Okay? Great. So guys, see you next Monday. And before next Monday, send me this list. Okay? I will be very happy to receive your email with your answers. Have a great week and see you on Monday. Bye-bye.
Ciao.
Ciao.
Bye.